This content is produced by DarkNetBreaker, a cybersecurity and dark web education brand. All videos, posts, and content are strictly for educational and awareness purposes only. We do not promote, support, or encourage any illegal activity. Our mission is to expose digital threats, protect online users, and educate the public about cybersecurity risks in the modern world. Stay ethical. Stay protected.
This visualization represents a multi-hop proxy breach at a zero-trust enterprise perimeter. In this context, the Tor network functions as a multi-layered proxy that obscures the true origin of inbound requests, allowing traffic to bypass standard network edge filters. These capabilities are used to facilitate several stages of a modern intrusion. Traffic routed through the network can be used for initial reconnaissance, obtaining initial access to exposed services, maintaining command and control, and the covert exfiltration of data. Active malware families frequently exploit this architecture. Threat actors use onion duke to wrap legitimate executables with malware. The actor known as BTCM-ITM-20 has operated thousands of nodes to hijack cryptocurrency transactions, while the group KAX-17 focuses on middle relays to map user routes. These operations align with specific MITRE ATTK designations. Actors like Onion Duke and KAX-17 utilize technique T1090.03 for multi-hop proxy obfuscation and T1595 for conducting anonymous active scanning against target infrastructure. Because decentralized onion routing terminates at an unpredictable egress point, it creates a boundary threat model. This model complicates the effectiveness of static defenses and requires a shift in how security operations detect and correlate incoming traffic. This diagram illustrates the Diffie-Hellman key exchange. The client encrypts data in reverse order using keys KN3, KN2, and KN1. As data travels, each relay removes its specific encryption layer. At the exit node, the final KN3 layer is removed, transmitting unencrypted data as plaintext. Malicious exit node operators exploit this exposure to execute protocol manipulation. They can use SSL stripping to downgrade secure sessions to unencrypted HTTP, or wrap legitimate binary downloads with custom shellcode to distribute malware. In this model, the exit node is an active inspection boundary. When internal circuit encryption is stripped away, the security of the communication relies entirely on the transport protocols implemented by the client. A common misconception in network engineering is that an adversary must control the exit node or break the encryption to de-anonymize Tor traffic. The Raptor attack model demonstrates that de-anonymization is possible through asymmetric routing. Because paths are often asymmetric, the route traffic takes from a server to an exit relay frequently differs from the route it takes back. This shows the Georgia Tech campus representing a baseline autonomous system. An entry relay here creates a stable path an adversary can monitor for traffic baselines. An adversary executes a BGP interception attack, announcing a more specific network prefix to hijack and reroute traffic through a hostile autonomous system. Observing both entry and exit points, they perform a correlation attack, matching TCP sequence numbers across both ends to de-anonymize the client. This demonstrates that payload encryption does not prevent de-anonymization if an adversary can manipulate BGP routes to observe the timing and size of traffic flows across the internet topology. Tor attempts to mitigate traffic analysis through network perturbation. This adds a layer of defense by introducing noise into packet timings and sizes to make manual correlation difficult. Modern frameworks like DeepCore and Rector use convolutional neural networks to bypass this noise. These models treat network flow features as time series data, allowing them to find patterns that manual analysis would miss. These models organize the data into a two-dimensional array matrix, labeled Fij, allowing the network to compare ingress and egress flows to find hidden similarities. Utilizing attention-based multiple instance learning, models like Rector extract accurate flow representations even when observed data is incomplete or heavily obfuscated by network latency. The success of these deep learning models indicates that network noise alone is no longer a guaranteed barrier against an adversary attempting to match ingress and egress traffic. Static IP blocklisting is often ineffective against Tor because exit nodes are temporary and frequently change. The mandatory staging phase for new relays ensures that the list of active exit IPs is in a state of constant churn. A more effective defense involves behavioral heuristics. tools like App ID can be configured to inspect SSL handshake patterns and specific cipher suites that identify Tor routing traffic, regardless of the source IP. Web application firewalls can also detect the high-velocity connection attempts associated with MITRE technique T1595.001. By monitoring these patterns, defenders can identify scanning activity coming from temporal nodes. Moving away from static indicators allows security teams to build a defense based on behavioral telemetry, mapping network activity directly to known attacker methodologies in the MITRE ATTK framework. This pipeline identifies multi-hop proxy threats. At the firewall edge, external dynamic lists update every 30 minutes. Next, CAPTCHA tests throttle automated scans. Finally, inside the SIEM, analysts write Custo query rules to detect authentication anomalies and correlate traffic with known exit node registries. A critical alert in this playbook is a successful cloud application or SSO login originating from a Tor exit IP. These events are high-confidence indicators of session hijacking or the use of compromised credentials. By combining dynamic edge controls, behavioral heuristics, and host-to-exit correlation, security teams can secure the enterprise perimeter against the risks of decentralized routing networks.